Hello everyone. In this video, let's wrap up Chapter 2. We will dive into the final three parts: model evaluation, hyperparameter tuning, and deployment maintain the system. Let's get started. First, let's test our data using a linear regression model. I have kept only the essential code from the previous video. Here, we create a pipeline that pre-processes the data and fits the model. Let's walk through the scikit-learn document together to understand the key functions: fit, fit transform, and predict. The fit function fit all the transformers one after the other and sequentially transform the data. Finally, fit the transform the data using final estimator. Fit transform function is fit the model and transform with the final estimator. Predict function transform the data and apply predict with the final estimator. In our linear regression pipeline, the fit function calls the preprocessing transformer fit transform, then fits the linear regression estimator on the transformed data. The predict function is called only on the final estimator, which is linear regression. Now let's train the model on the entire training set and test it on the first 5 rows. The result is not so great. The root mean square error, RMSE, it quantifies the difference between predicted value and actual values, providing a sense of how far off the predictions are on average. The smaller RMSE, the better model is. It is a common metric for regression models. It's around 68,000. Not a good number. We use a very simple model to predict the complex dataset. This is typical underfitting. We should use a more powerful model. Let's try the decision tree. Replace linear regression with a decision tree and check the result. The result becomes 0. This means the decision tree fits every single data point perfectly. Essentially, we use a trained dataset to train the model and test its results with the train set gives 0 error. This is not a good strategy to evaluate model performance. We need to use cross-validation to better evaluate model performance. Scikit-learn provides a k-fold cross-validation feature. Here, we split the trained data into 10 folds, train on 9 folds, and evaluate on 1 fold. We repeat this process 10 times and take the average RMSE. For decision tree, the result is similar to the linear regression. It is not great. Let's try random forest and see how it behaves. Pretty much similar like before, and use the cross-validation to get the final evaluation. But runtime is extremely long. The end result is better than the previous 2 models, but still not good. The bad performance is caused by the overfitting. We need to tune our model and hopefully get better results. One way of doing this is try all kinds of hyperparameters. It is a time-consuming and tedious job. Scikit-learn provides great search. It will try all the combinations provided by the user and use cross-validation to evaluate all possible combinations. In our code, scikit-learn splits on the double underscore. Preprocessing GeoN clusters breaks into 3 parts: preprocessing, geo, and N clusters. Scikit-learn traces each name. It goes into the preprocessing column transformer, geo transformer, and changes the parameter N clusters to those candidates. Random forest max feature is similar. It goes into random forest estimator and substitutes max features parameters with those candidates. This grid search tries 3 different N clusters with 3 different max features, with 9 different combinations plus 2 times 3 as a different combinations. Then each combination with 3 folds, in total 45 rounds of training to get the best hyperparameter combination. By default, it gives a negative score, and let's reverse them for readability. So far, we got the best RMSE. Grid search only searches on smaller combination. sklearn also provides RandomizedSearchCV. It is a preferred way to test more combinations. Let's check it out. The n-iter means the function randomly chooses 10 different combinations from given ranges. The random int gives a range for the search algorithm to try values. The final result shows 47 geoclusters combined with 13 random forest max features gives the minimum RMSE. Very cool. RandomizedSearchCV helps us find the lowest RMSE so far. The feature importance of random forest regression helps find out the relative importance of each attribute for making accurate predictions. From the result, we can see the relative important feature is log mean income. With the information, we can probably drop less useful features. Now we have finished the hyperparameter tuning. We can finally evaluate our data on a test set. Remember, we set aside this stratified test set at the very beginning. It is time we can test our model and get final performance of our model. The test RMSE is even better than the validation RMSE. This means our model can generalize pretty well on unseen data. Now it is good time to save our model to a file, and when we want to ship to production, we can load it from the file system to start predict new data. We use joblib to save our model into a file. Then let's load it from file system and continue to make predictions. The example uses the first few rows to make prediction. At the current point, we finally have our model ready. In a real-world application, we can load the model into the web server. User can send attributes through web server REST API, and our server simply call the model to make the prediction. We can also upload models to cloud storage and ask third-party platforms to help us host and scale the model, such as Vertex AI. Our backend can talk to those hosting platforms and get the prediction. In reality, the real-world housing data is constantly updating. We still need to keep eyes on our model performance and constantly update our model. This requires setting up some monitoring system and constantly check metrics for our model. When the prediction metrics start going down, it might indicate the model needs to be retrained on the fresh data. Most of the time, the data keeps evolving. We need to regularly retrain the model with the updated dataset. All of this requires a good ML infra as a support to constantly monitor and automate the process. Now we have finished all the concepts covered in chapter 2. Lots of good things we have learned, and thanks for watching. And I will see you in the next video.